I'm Hongjiu from University of Michigan. It's a great honor to present our winning algorithm on behalf of Team Guan Lab, and we are glad to share our idea about using tumor heterogeneity inference using density-based mixture model. So this tumor or cancer enthusiastic starts back to the days in Reagan's age, and 40 years past, we haven't made enough process to cure the cancer. And this thing is complex. Different people might carry different kind of tumor, and even within the same patient, the composition of the tumor sample is different. They have normal cells, immune cells, and also tumor cells. And tumor cells might diverge into multiple subclones. It's making the whole thing really complicated. And to make it worse, they might carry some drug resistance mutations. So people who want to design therapy, they must know how complicated the tumor is. So it's very demanded to infer the tumor heterogeneity. And the first question we usually think about is it possible we can cluster somatic mutations presented in the tumor sample into multiple subclones? And it's actually represented in the subchallenge 1 and 2, a very important question. One of the hints we have from the challenge data is the distribution of the allelic frequency. So this is one of the training sets we have. And you can see the peaks represent somehow related to the subclones. And is actually matching perfectly. One of the subclones is 0.9, and here the peak is around like 0.45. So there's kind of a relationship going on there. And most people will use Dirichlet process to infer this information. And I guess the previous talk just showed a great example of applying Dirichlet process to do that. Actually, most widely used like PyClone and the PhyloWGS, these tools also use a similar process. They might introduce some variation like the so-called tree-structured steep breaking process. It's incorporating the phylogeny information into the likelihood function. So also very efficient inferring both clusters and the phylogeny at the same time. But for us, we are pretty new in this area. When we participate in competition, we don't really have an existing tool to tune. And in order to infer Dirichlet process, most of the cases you need to rely on Monte Carlo simulation, which is relatively slow. And when you implement that, you need to take extra effort to make sure you're implemented right. So when we want to set up a faster pace, iterative testing process, we want something simpler. So we look at the density, the histogram, and say, the peak represents individual subclone. Why not we just smooth that histogram? So we basically use the density estimation to build up a density function, look at the curve and say, okay, there are 2 peaks there. I guess there are 2 subclones. Very straightforward, but to me, I think it's also an elegant way. But one concern we have is maybe you have some smaller subclones that are carrying only a few mutations, and you might miss it. So in this case, we are showing a comparison of calling conservative results versus aggressive results. You can call more subclones or fewer subclones. The area here corresponds to the number of mutations. The density means how many mutations lies within this range of allelic frequency. So as you can see, on the left is you call less clusters or less subclones. On the right is more subclones. It's about the same amount of misassignments you might make. However, on the right side, you're disrupting the co-clustering relationship between the mutations in the rest subclones. So originally, those subclones, when you call it, you might assign them together. But here, because you try to find the so-called third subclones, you are only choosing those mutations have very similar and very close allelic frequency to your prevalence, and pick it up and assign them to separate subclones. You're disrupting this co-clustering relationship. And I think that's the key point when we solve the Subchallenge 2, which is measured in terms of co-clustering matrix. So here's a detailed description of our solutions. And actually, when I heard the previous talk from GSIR team, we are very similar in many cases. So BAF is a great information for us to infer the cellularity of the whole tumor content, or on the other hand, the normal contamination ratio. So the first two equations shown here using BAF to infer the cellularity is actually originally derived in Tumour's team when they published the Phylogeny paper. And we extend that to the two-state copy number variation. If you have subclonal copy number variation, actually they provide you more information about it because you don't have to use integer programming or something to round the value. And if you notice that, this can actually give you the exact result as the official cellularity file. So in our submission, we don't really use that file. In the second subchallenge, we use the density estimation to build up the curve. And there's one problem about it is some of the allelic frequency is complicated by the copy number variation. So when we incorporate that, we need to enumerate all the cases, whether they're on the major allele or on the minor allele, or they are actually not duplicated. We calculate all possible allelic frequency for that. And we correct it, and we do the optimization using, say, expectation maximization. So based on that, we do the assignment. We can use Gaussian model to model the noise. We can use binomial model to model the noise. Actually, we tested both. Performance is like 0.001 difference, so they're very similar. And the power here is because you use density, you already narrowed or you already fixed the number of the cluster. So you basically are inferring some kind of exponential family distribution. Then you don't really need multicolor simulation, and you can just use EM, or in actually Dr. Yuanfang Guan's implementation, she just picked up the value of the density and clustering into like a 3 or 4 subclones based on the curve. They don't even use a likelihood function to infer that. And it's also performing very well. And we think it's a great clue to borrow information from this curve. With that, then you can use some membership probability, either using a Gaussian model or binomial model. You can calculate that and see which subclone is more likely to carry this mutation. And after that, you can calculate the co-clustering matrix and ancestor matrix using simple linear algebra strategy. You multiply the probability matrix by its transpose, you get the 2A's result. You multiply that by the adjacent matrix and the transpose of probability matrix, you get the 3B results. It's pretty accurate. One thing that I found interesting is, so many people using a binomial model, a beta binomial model, and this thing, and Gaussian model. So a lot of the time, I think the Gaussian model is, simple, rudimentary, but why it is working here? So I asked Yuanfang, and she's like, who is your most favorite mathematician? I say like Euler, probably Euler and Gauss. And she's like, yeah, that's right. He's a elegant person. And when we look back to his work, Gaussian distribution is a wonderful model for determining the errors, determine the experimental deviations, and when you have enough data follows binomial distribution, you can asymptotically assign that to a Gaussian distribution at the same time. So it's a elegant way and often being overlooked, but we really benefit from this. It's our 10 marks to Gaussian approach. And unfortunately, they no longer use marks, they use euro nowadays. But with that kind of assignment, then we want to ask how to infer the phylogeny there. And we think it's a really hard question. So actually, in Tumour's paper, we found that given one sample, it's almost impossible you can identify the exact phylogeny inference. For example, in this specific case, say you have 3 subclones, 0.8, 0.4, 0.2. You can actually build 2 equivalent phylogeny. First one, say it's a linear. Second one, you say the 2 smaller subclones are child of the biggest subclone. they are all correct, and you cannot find a way to disambiguate these two the phylogeny, unless you have some kind of assumption. So, I'm really surprised that both our teams think about using greedy algorithms, starting from the biggest subclone and goes to the smallest subclones, and we assign them back to the tree. The only difference is we prefer use a beta distribution here, and it's actually derived from the tree structured stick breaking process. Is equivalent, as you already fixed the number of a cluster and fixed the assignment. So the idea is, if you assign, say, subclone 2 to subclone 1, and the proportion of the smaller subclone against the bigger subclone should follow some kind of a distribution here. And here we choose beta distribution because it's it has a higher variance, and we kind of give a flexible restriction on this data and let the likelihood function pick up the best one. And we perform decently well on simulated data. So here's a summarized results on all the training data we have. We have a huge margin over MyDPC on Subchallenge 1 and Subchallenge 2, and we give a decent result on Subchallenge 3. It's more about the easier model you can handle, and also accelerate the testing phase and try to incorporate new functionality or new parameter into this model, and we think that helps a lot. So we also do some experiments on a real-world tumor after the challenge, and it's very interesting. We got the data from our collaborators in Peking University and the Cancer Center in our University of Michigan. Great, we're really great to them, and this data is one of the sample we get from the patient. So here is the distribution of the allelic frequency. As you can see, there are several peaks over there. Somehow, if you look at it by eye, you can tell there are some subclones in it. And we're comparing our algorithms to a existing algorithm they are using in their analysis. It's also decently fast. We can pick up the top two subclones here where they are missing. And one of the reasons we found is that they're kind of unconfident when they call those top subclones because they carry somehow smaller number of mutations. But in our cases, when we look at it, we inspect it, there is a huge gap between these two subclones, and we think it's very confident you can call them. And there's a, it's amazing. We can see like there's a huge difference between different colors, and we are fairly confident our call is pretty good, and we actually match them with the expert panel, and they say, you know what, we believe what you're calling, and the first two subclones should be there. And there are some trivia we would like to share about our algorithm. So first one, the subchallenge 1B to infer the number of cluster we think is really hard, and because the nature of this challenge is in the simulated data we have a specific number of subclones, and we want to kind of infer that number, and for a long time we don't have any clue how to do that, and we kind of think it's a fortune telling. And 1C is actually important if you want to infer that, because they give you, it's actually the core of the subchallenge 2 and subchallenge 3. One thing that is important in this subchallenge is to infer the false positive mutations, and I noticed that they use some kind of rule-based method. We just throw all the mutations into a random forest that pick up the allelic frequency used as a feature and let it to do the prediction. We also prefer mutations in the non-copy number variance region, similar to GSIL's approach, which choose the mutations in copy number equal to 1 regions. For those regions, the inference can be a lot simpler. Actually, that can reduce the Dirichlet process back to some exponential family mixture model, and you can use EM to infer that. One key factors we found in this challenge is numerical stability matters. It's all about implementing the correct equations and implement them correctly. It's easier said than done, and we face a lot of problems when the floating number getting too small and we have to fix it manually. Have to be very careful about picking the correct function to do the numerical computing. To summarize our work, we use kernel density estimation as an alternative strategy to the Dirichlet process inference, and it accelerates a lot, helping a lot when we do this faster paced testing iteration. The reduced phylogeny inference model really helps a lot, and we think the assumption there is acceptable, but we definitely prefer having multiple samples to infer the phylogeny. And this challenge is quite different from many past dream challenges. It's not a typical machine learning challenge. On the other hand, it's more about implementing tools and introducing the correct functionality, implement them correctly, and be careful about all the corner cases. And Paul just mentioned most of the teams have like 0 in that challenge. We believe we might also have, and it's a great challenge for us to handle all the corner cases. It's, to be honest, it's very challenging. I would like to acknowledge Dream competition organizers, the IBM Research and Sage Bio Network. They have been very helpful. Without them, we cannot do this kind of work, and it's very exciting. For specifically this heterogeneity challenge, we really appreciate Dr. Paul Bontres. He's been helping a lot on scoring and answering questions on the forum. Andrian and Kyle Elrod have been helping a lot about debugging the Docker and reporting all the errors to us in the first few rounds of leaderboard. We also appreciate Dr. Jun Li and Dr. Yang Ke's lab. They provide us chances to do post-challenge analysis, and also Erich Nayan's lab. We have a great post-challenge collaborations on this topic. Special thanks to Dr. Yuanfeng Guang, and I really enjoyed my time in her lab, and we had a wonderful talk every day about basic data science. Data science can't be more enjoyable. My fellows, Rivan Aski, Barrett Palmer, and Jen Lan, my lab mates, they helped a lot during the challenge. Also, I'd like to thank my thesis committee, Margit Burmeister and Gil Oman. They help a lot about setting up the post-challenge analysis and the collaborations. That's all to my talk, and I'm willing to take any questions.
It's one for all the performers and organizers. So I guess this challenge is really nice, really good, and kind of benchmarked on relatively clean simulated data and so on. But I guess we're facing a challenge of trying to do this kind of reconstruction from using a targeted platform from an FFP block where we have no matched normal to understand the variance on the platform and how that relates to the copy number and so on. Have you guys thought about kind of taking this to the next step and trying to tackle some of those real life problems?
That's me. So that's what we're planning for SMC Het 3. SMC Het 2 is going to be looking at spatial heterogeneity. What do you do if you have multiple samples together and merge them? And then 3 is going to be an attempt to do it from targeted panels. The subclonality from targeted panels is likely going to be even harder than this challenge. And seeing that for some of the challenges, the winning submissions had scores of 0.4 and 0.5, suggests that there may actually be a need for more algorithm development on clean data before it's worth going into even noisier data. I had a question.
Yeah.
So I'm trying to follow how you decided on the number of densities to use. So you could have, in some cases, these hidden densities, and did you just always go with parsimony, or was it a little more model-based than that?
Great questions. I mean, I think we are even more conservative than parsimony assumption. So there are a few requirements. First of all, if these cluster only carrying, let's say, 1 mutations or 2, we probably won't call that. It's probably more like a noise. And second, so we first estimate the cellularity. So if we found any peaks that is beyond the cellularity by, say, 0.1, we believe that's kind of a noisy data or some data we didn't process well, and we will drop them. For the rest of them, we strictly follow the parsimony assumption. We only call the smallest number of clusters, and we think it's helping a lot to keep the co-clustering relationship between the mutations.
Thank you.
Thanks.